The Cosmic Web, Chapter 1. The Architecture of the Universe. Close your eyes if you like, or let them grow heavy. Let your body settle into wherever you are resting right now. There is nowhere you need to be, nothing you need to do. For the next little while, all that exists is this moment, this quiet, and the soft unfolding of one of the most breathtaking stories ever told. It is not a story from a book, or a dream, or a myth. It is the true story of the universe itself, told in the language of light and gravity and deep, patient time. Tonight, we are going to travel together to a place so vast, so ancient, and so quietly beautiful that simply thinking about it has a way of making everyday worries seem very, very small. We are going to explore the architecture of the universe. Not just the stars, not just the galaxies, not even just the galaxy clusters, but something even grander than all of those things combined. We are going to explore the largest structure in all of existence. A structure so enormous it makes galaxies look like grains of sand. A structure so intricate and so elegant that scientists who have spent their entire lives studying it still feel a sense of childlike wonder every time they look at it. It is called the Cosmic Web. Let that phrase rest in your mind for a moment. The Cosmic Web. Even the name carries something soft and mysterious about it. A web. Something woven. Something delicate yet vast. Something that connects everything to everything else in a pattern so complex it stretches beyond the limits of our imagination, and yet so organized, so deliberate in its form, that it almost feels like the universe itself had a plan. Here is the first thing to understand, and it is something that may gently shift the way you think about everything you have ever looked up at in the night sky. The universe, at its very largest scales, is not random. When you look at the stars scattered across the sky on a clear night, it might seem like they are simply thrown there, like glittering dust tossed from an open hand. But that appearance is deceiving. Pull back far enough, look at scales large enough, and something extraordinary comes into view. The universe is organized. Deeply, profoundly, beautifully organized. On the grandest scales we are capable of observing, the cosmos is not a chaotic jumble. It is a vast, interconnected network. A structure of almost unimaginable complexity and almost heartbreaking elegance. Everything in the universe, every galaxy, every cluster of galaxies, every wisp of gas floating in the dark between the stars, all of it is part of this single, enormous, living architecture. And the shape of this architecture is something quite poetic. Astronomers, when they first began to map it, found themselves reaching for an unusual comparison. The cosmic web, they said, looks like a sponge. A vast, three-dimensional sponge glowing softly in the dark. Or perhaps even more evocatively, it looks like a spider's web. Not a flat web stretched between two branches in your garden, but an infinite, three-dimensional web stretching in every direction simultaneously, looping and connecting and branching across distances so large that our minds have no real framework for understanding them. Try, if you like, to picture it. Imagine you are floating in space, but you have somehow been given the ability to see at scales that no telescope has ever quite managed. You are looking at a region of the universe perhaps 1 billion light years across. And what you see when you look at it all at once is this softly glowing lacework. Threads of pale light stretching out in every direction, bending toward each other, joining at brilliant, dense clusters. And between those threads, vast, almost perfectly empty regions of darkness. The whole thing looks alive, somehow, like the web of nerves inside a living creature, or the branching of a great river system seen from very, very high above. Those glowing threads have a name. Astronomers call them filaments, cosmic filaments, and they are perhaps the most important structural feature of the universe as a whole. A filament is, at its core, an immense thread of gas and dark matter. Now, when we say immense, we mean something that really defies ordinary language. A single cosmic filament can stretch for hundreds of millions of light years. Hundreds of millions of light years. To give you some sense of scale, the distance from Earth to the nearest star beyond our Sun, the closest stellar neighbor we have, is about 4 light years. A single cosmic filament can be 50 million times longer than that. A single thread of the cosmic web could connect 50 million of those journeys end to end and still be reaching. These filaments stretch through the silent emptiness of space, patient and ancient, carrying the material that makes up galaxies, quietly connecting the universe's largest structures to one another across the void. And here is where things become truly beautiful. Galaxies, the great island cities of stars that populate the universe, do not simply float where they please. They are not scattered evenly or randomly through space like seeds thrown by the wind. Instead, galaxies cling to these filaments. They gather along the threads of the cosmic web the way water droplets gather on a spider's silk on a dewy autumn morning. Have you ever seen that, a spider's web covered in dew? The way each tiny drop catches the light, the way they seem to trace the invisible threads of the web, making a structure visible that was there all along but hidden until the water found it? That is, in a very real and not entirely metaphorical sense, exactly what galaxies are doing. They are the dewdrops. They are making the invisible web visible. So when you look at the night sky and see a star, you are seeing a dewdrop on a thread of the cosmic web. You are seeing a tiny part of the largest structure in the known universe. There is something quietly wonderful about that. Now, those threads, those filaments, do not simply trail off into nothing at their ends. They meet, they converge. At the places where filaments come together, where multiple threads of the cosmic web intersect and join, something remarkable happens. The density of matter increases dramatically. Gas pours in from multiple directions. Dark matter concentrates. And in these extraordinary intersections, the universe builds its most impressive creations. These intersection points have their own name. Astronomers call them nodes. And the nodes of the cosmic web are where the universe's largest galaxy clusters are born and spend their lives. A galaxy cluster is not a single galaxy. It is a collection of galaxies, sometimes hundreds or even thousands of galaxies, all gravitationally bound together, all swimming in a shared sea of superheated gas, all embedded in an enormous halo of dark matter. And the very largest of these clusters sit precisely at the nodes, the meeting places, the grand junctions of the cosmic web, glowing with the light of millions upon millions of stars. When you let your eyes drift across the night sky, it is worth knowing that somewhere in the depths beyond what you can see, those brilliant nodes exist. Places where the web of the universe has drawn matter together with such patient insistence over such vast spans of time that it has built the most massive gravitationally bound structures that physics will allow. But the cosmic web is not only defined by what it contains. It is equally defined by what it does not contain. Because between the filaments, between the glowing threads and the brilliant nodes, between the gatherings of galaxies and the slow rivers of gas, there is something else entirely. There is emptiness. These empty regions are called cosmic voids. And they are not merely gaps, not simply spaces where the galaxies happen to be fewer. They are vast, almost perfectly empty bubbles of space. A single cosmic void can span hundreds of millions of light-years in every direction. You could travel through one for longer than the universe has been old and still not reach its far wall. Inside a void, there are almost no galaxies at all. Almost no gas. Almost no dust. Almost nothing. Just space, unoccupied and silent, bounded on all sides by the distant glowing threads of the web. The voids and the filaments together create the structure that gives the cosmic web its sponge-like quality. The filaments are the solid material of the sponge, and the voids are the open spaces within it, the holes that make the sponge what it is. Together, they define the shape of the universe at the largest scales we know. Now, the filaments of the cosmic web are not made of stars, not primarily. Stars are relative newcomers, built inside galaxies from material that was already there. The web itself, in its fundamental form, is made of gas and dark matter. The gas is the visible portion, the part that astronomers can, with great ingenuity and effort, actually detect and study. And this gas is remarkably thin, remarkably diffuse. In the filaments, the density of gas is only slightly higher than in the surrounding voids, which are themselves nearly empty. The intergalactic medium, as this diffuse gas is known, is so thin that if you could take a cubic meter of it and bring it back to Earth, it would be a far better vacuum than the best vacuum we have ever been able to create in a laboratory. And yet, even in its extraordinary thinness, this gas has a composition that is deeply meaningful. The gas that threads through the cosmic web is mostly hydrogen and helium. Those are not just any elements. They are the oldest elements in the universe. They are the elements that were forged in the first few minutes after the Big Bang itself, when the universe was so hot and so dense that nuclear fusion was happening everywhere simultaneously, building atoms out of the raw energy of creation. Every atom of hydrogen in a cosmic filament today is a relic of those first moments. It has been traveling, drifting, cooling for 13 billion years. It is, in a very real sense, among the oldest material in existence. And speaking of 13 billion years, let us think for a moment about time. Because the cosmic web is not a young thing. It is not something that appeared recently or suddenly. It has been slowly forming and evolving for over 13.8 billion years. For the entirety of the universe's existence, this great structure has been quietly assembling itself. To understand how it began, we have to go back to a moment so early, so close to the beginning of everything, that the universe was not yet even a fraction of a second old. In those first unimaginably brief moments after the Big Bang, the universe was an almost perfectly uniform sea of energy and matter. Almost perfectly uniform, but not quite. There were tiny variations, tiny ripples in the density of matter, places where the energy was very slightly more concentrated and places where it was very slightly less. These variations were extraordinarily small, almost vanishingly small. They were quantum fluctuations, the result of the strange probabilistic nature of physics at the smallest scales, frozen into the fabric of the expanding universe. But small as they were there. And they were enough. As the universe expanded and cooled over millions of years, and then hundreds of millions of years, these tiny initial ripples began to grow. Gravity, patient and inexorable, began its long work. Matter, ever so slowly, began to fall toward the regions that were slightly denser. It was an imperceptibly slow process at first. But time, as we have noted, was not in short supply. Over billions of years, a slow tug of gravity pulled matter into these intricate, thread-like structures. The slightly denser regions grew denser. The slightly emptier regions grew emptier. The tiny initial ripples in the fabric of the early universe were amplified over cosmic time into the grand architecture we see today. The cosmic web, in other words, is the grown-up version of the universe's very first fingerprints. The structure you would see if you could look at the entire observable universe from outside is a direct echo, amplified and elaborated over 13 billion years, of the quantum fluctuations that existed in the first fraction of a second of time. That connection between the quantum world of the very small and the cosmic architecture of the very large, between the smallest possible variations and the largest possible structures, is one of the most profound things science has ever revealed. The filaments you might someday see in a visualization of the cosmic web, those vast threads of glowing gas stretching across hundreds of millions of light years, were seeded by events that took place at scales many billions of times smaller than an atom. Now, how do we know any of this? The cosmic web, after all, is not something you can simply point a telescope at and photograph. The filaments are so diffuse, so thin, that they emit almost no light of their own. The gas is too cold and too spread out to glow in visible light the way a star does. For a long time, the cosmic web was almost entirely theoretical, something that the mathematics of gravity and cosmology predicted must exist, but that was extraordinarily difficult to actually see. One of the most elegant methods astronomers have developed for mapping it relies on a phenomenon called the Lyman alpha forest. The idea is this: scattered across the universe, at enormous distances, are objects called quasars. Quasars are extraordinarily luminous cores of distant galaxies, powered by supermassive black holes consuming matter at prodigious rates. They shine so brightly that we can see them across most of the observable universe. And the light from those distant quasars, on its long journey to our telescopes, passes through the filaments of the cosmic web. As it passes through the gas in those filaments, some of that light is absorbed. Hydrogen atoms at different distances along the line of sight absorb light at slightly different wavelengths, because the universe's expansion shifts the wavelength of the light as it travels. And this absorption creates a characteristic pattern in the spectrum of the quasar's light when it finally arrives at our instruments, a series of dark lines and troughs that astronomers call the Lyman alpha forest. By analyzing this forest of absorption lines, astronomers can essentially map where the gas filaments are along the path between us and the distant quasar. They can reconstruct the distribution of matter in 3 dimensions, building up a picture of the cosmic web from the shadows it casts in the light of distant objects. It is a remarkable technique, almost like X-raying the universe, using the light of ancient luminous beacons to reveal the invisible architecture in between. And the maps that have been built this way are stunning. They show a universe organized at the largest scales into exactly the kind of web-like structure that the theories predicted. The filaments are there. The nodes are there. The voids are there. The whole grand architecture, assembled over 13 billion years from the tiniest quantum ripples, laid out in the data for anyone with the patience and skill to read it. There is one more thing to say about the cosmic web, and it is perhaps the most quietly astonishing thing of all. scientists studying the large-scale structure of the universe have noticed something that many of them find almost impossibly poetic. The cosmic web, this vast network of filaments and nodes and voids spanning the entire observable universe, bears a striking and beautiful resemblance to something much closer to home. It looks, in its structure and its organization, remarkably like the neural network of a human brain. The branching, connecting, clustering structure of the cosmic web and the branching, connecting, clustering structure of neurons in the human brain look, at certain scales, almost identical. Both are networks of interconnected nodes with thread-like connections between them. Both have dense, highly connected regions separated by sparser regions. The patterns of connectivity in both systems follow similar mathematical laws. This is not, to be very clear, evidence of anything mystical or supernatural. The similarity arises because both systems are governed by similar mathematical processes, by networks that grow and connect according to rules that produce this kind of branching structure. But that does not make the resemblance any less beautiful. The universe's largest known pattern and the universe's most complex known object, one spanning billions of light years and one sitting inside a skull, look, in a deep structural sense, like echoes of each other. As you rest now, let yourself imagine the light that is traveling toward us at this very moment from the farthest reaches of the cosmic web. It left its source billions of years ago, long before the Earth existed, long before the sun had formed, setting out across the expanding darkness on a journey that would take longer than our entire solar system has been alive. And now it is nearly here, still carrying within it the signature of the filaments it passed through, still encoding in its wavelengths the shape of the web it traveled across. When astronomers point their instruments at the sky tonight and capture that ancient light, they are reading a letter written by the universe to itself across an almost incomprehensible span of time. And consider this, our own galaxy, the Milky Way, our home among homes, the island of stars we belong to, is itself just one tiny participant in all of this. We sit along a minor filament of the cosmic web, one branch among billions, one dewdrop on one thread of the vast and ancient silk. From a cosmic perspective, the Milky Way is completely unremarkable in terms of its position. It is not near a great node. It is not at the center of anything. It is simply here, going along a filament, part of the pattern, one small piece of an architecture that stretches away from us in every direction further than any light will ever travel in any direction from this place. There is something deeply calming in that thought, if you let it settle. We are part of something so much larger than ourselves that the word large barely begins to describe it. The worries of the day, the small frustrations, the plans and the anxieties, all of it belongs to a creature living on a small rock, orbiting an ordinary star, tucked along a minor filament of the largest structure in the known universe. And that structure itself is still changing, still growing, still evolving, as it has been doing for every moment of the 13.5 billion years since those first quantum ripples were stamped into the fabric of a newborn cosmos. Even now, as you breathe slowly in this quiet moment, the web is stretching. The universe continues its eternal expansion, carrying the filaments further apart over time, stretching the web across ever greater distances. The voids are growing. The filaments, in a sense, are becoming thinner and more spread out as the universe grows. The architecture is not frozen. It is alive in its own slow, cosmic way, changing on timescales so vast that a human lifetime, or even the entire history of human civilization, amounts to less than the blink of an eye. But in this moment, and in every moment, the web is there. Patient, ancient, beautiful, holding the universe together in its vast and luminous embrace. The largest known pattern in all of nature, woven from quantum whispers and billions of years of gravity's quiet, insistent work. Let that image be with you as you drift. The filaments of the cosmic web stretching away in every direction from where you lie. The galaxies clustered along them like soft lights in the dark. The vast, quiet voids between. And somewhere in all of that immensity, one small blue world, spinning slowly, with you on it, resting, breathing, letting the universe hold you for a while. There is nowhere else you need to be. The web is ancient and it will go on long after any of us are here to wonder at it. For now, let your thoughts become as soft and as diffuse as the intergalactic gas in the filaments. Let them spread out. Let them thin. Let the vast quiet of the cosmos be your quiet too. The universe is organized. It is not chaos. From the very first fraction of a second, it has been building toward this extraordinary pattern, this grand web of light and matter and dark, patient gravity. And you, in this moment of rest, are part of that pattern. You are made of the same hydrogen that drifts in the filaments. The atoms in your body were forged in stars that lived and died along the threads of the cosmic web. You are not separate from it. You are woven into it. Let your breathing slow. Let your thoughts drift gently, like gas along a filament, like a galaxy following the slow current of the web. There is nothing required of you now except to rest, and to let the universe be as large and as quiet as it is. We have only just begun our journey through the cosmos. There is so much more to discover, so many more structures to explore, so many more wonders waiting just beyond what we have already seen tonight. But for now, simply rest here at the beginning with the image of the cosmic web spread out across the darkness above you. Vast, ancient, beautiful, patient beyond all reckoning, and perfectly quietly at peace. Chapter 2, The Invisible Scaffolding. Let yourself settle a little deeper now. If your body has found a comfortable place to rest, let it sink further into that comfort. Let your shoulders drop. Let your jaw unclench. Let the soft weight of your limbs remind you that you are held, that the ground is here, that nothing is required of you in this moment except to breathe and to listen. In the last chapter, we began to trace the great architecture of the universe. We followed the glowing filaments of the cosmic web across distances so vast that even the word vast does not quite do them justice. We watched in our imagination as galaxies clung to those threads like drops of dew on silk, and we marveled at the grand, sponge-like structure of everything, the bright nodes, the quiet voids, the slow, patient weaving of gravity over 13 billion years. But there is something we have not yet spoken about. Something hiding in plain sight, or rather, hiding in a kind of sight that no eye has ever possessed and no instrument has ever quite achieved. Something that is present everywhere we have looked, fundamental to everything we have described, and yet utterly, completely, profoundly invisible. Tonight, we turn our attention to the true foundation of everything we have seen so far. The invisible scaffolding upon which the entire cosmic web is draped. The ghost architecture beneath the visible universe. We are going to talk about dark matter. Here is something worth pausing on as you breathe slowly in the quiet. Everything you have ever seen, every star in the night sky, every photograph of a distant galaxy, every glowing nebula, every cluster of lights in a long-exposure image of deep space, all of the light and color and visible matter in the entire observable universe, all of it together adds up to only a tiny fraction of what is actually out there. A small fraction, a minority, a thin, luminous skin over something far more massive and far more mysterious beneath. The glowing galaxies and the gas we can detect, the ordinary matter that makes up stars and planets and people and everything we have ever touched or seen or measured, all of it accounts for only a small portion of the total matter content of the universe. The rest, the vast, overwhelming majority of all the gravity-producing matter in the cosmos, is something else entirely. Something we cannot see. Something we cannot touch. Something we have never directly detected with any instrument ever built. It is called dark matter, and it makes up approximately 85% of all the matter in the universe. Let that settle for a moment. 85% of all the matter that exists, of all the substance and stuff that makes up the physical universe, more than 4/5 of it is something invisible, something undetectable by any direct means, something that has been present since the very earliest moments of the cosmos and yet remains, even now, one of the deepest mysteries in all of science. The universe, it turns out, is made mostly of something we do not understand. And the word dark in dark matter is not a poetic choice. It is a precise one. Dark matter does not emit light. It does not glow, not even faintly. It does not reflect light the way a moon reflects the sun, and it does not absorb light the way a dark cloud blocks what lies behind it. It is not dark the way a shadow is dark, or the way a starless night is dark. It is dark in the most absolute and fundamental sense. It simply does not interact with light at all. Light passes through it without any effect, as if the dark matter were not there. You could shine the most powerful flashlight in the universe directly through a wall of dark matter 1,000,000,000 light years thick, and the beam would emerge on the other side completely unchanged. And yet, and this is the beautiful and slightly eerie thing, we know it is there. We know it with a confidence that astronomers rarely feel about anything so mysterious. We know it not because we can see it, but because we can see what it does. We know it is there the same way you might know that a vast invisible hand is pressing against a curtain, not because you can see the hand, but because you can see the curtain moving, pushed into shapes that nothing visible could explain. The thing that moves the curtain of the visible universe, the presence we detect through its effects rather than its face, is the gravitational pull of dark matter. Gravity is how dark matter announces itself. It does not speak in light. It speaks in the language of mass, in the bending and curving of space, in the gentle but inexorable pull it exerts on everything around it. And because we can measure that pull with great precision, we can map where the dark matter is, how much of it there is, and what it is doing, even though we cannot see a single particle of it directly. One of the most fundamental things dark matter does, one of its most essential roles in the story of the cosmos, is this. Every single galaxy in the universe, including our own Milky Way, is surrounded by a massive, invisible structure called a dark matter halo. Picture our galaxy, that beautiful spiral of a few 100 billion stars that you belong to, and then imagine wrapped around it an invisible sphere of dark matter, vastly larger than the visible galaxy itself. The stars and gas and dust that we call the Milky Way extend for perhaps 100,000 light years in diameter. The dark matter halo surrounding it extends perhaps 10 times further in every direction. It is immense, it is invisible, and it is absolutely essential. Without that halo, without the gravitational embrace of all that dark matter, our galaxy would not exist in its current form. And here is why. A galaxy like the Milky Way is spinning, not slowly either. Our solar system is orbiting the center of the galaxy at a speed of roughly 800,000 kilometers per hour. At that speed, ordinary physics, the physics of just the visible matter, the stars and the gas, would predict that the outer parts of the galaxy should be flung outward over time, that the centrifugal tendency of a spinning system should gradually overcome the gravitational pull holding it together and scatter the outer stars into the void. But that is not what we observe. The outer parts of galaxies spin just as fast as they should if there were far more matter present than we can see. The galaxies hold together. The stars stay in their orbits. Something is providing the extra gravitational glue. Something is holding the whole spinning system together, and that something, present everywhere in and around the galaxy, providing a steady, firm gravitational embrace that the visible matter alone could never supply, is the dark matter halo. Dark matter, in this sense, is what makes galaxies possible. It is the cosmic glue, the invisible armature around which the visible universe is built. Without it, the spinning galaxies we see would slowly come apart, scattering their stars into lonely wanderers in the dark. With it, they hold together, they persist, they remain the great island cities of stars that populate the cosmic web. And dark matter does not merely cradle individual galaxies. It shapes the cosmic web itself. Remember the filaments we explored before? Those vast threads of gas and matter stretching for hundreds of millions of light years across the universe? Those filaments are not, at their core, made of gas. The gas follows the structure, yes, but it does not create it. The true substance of those filaments, the gravitational architecture that gives them their form and holds them in their shape, is dark matter. The filaments of the cosmic web are, at their heart, giant, flowing rivers of dark matter. Immense currents of this invisible substance, streaming along paths determined by the gravitational landscape of the cosmos, gathering and concentrating where multiple streams converge, forming the bright nodes we discussed before. The ordinary matter, the gas and dust, and eventually the stars and galaxies that form within them, all of it is simply responding to the gravitational invitation of the dark matter beneath. Ordinary matter falls into the valleys carved by dark matter's gravity. It pools there, it cools, it condenses, it builds structures. But it is always following the dark matter's lead. Think of it like a great invisible river system carved into the landscape of space. The dark matter carves the valleys and the channels. And then ordinary matter, following gravity as all matter must, flows down into those channels and fills them. The rivers of gas we can detect, the filaments of the cosmic web that we can map with the Lyman alpha forest, are flowing along channels that were carved by dark matter long before the gas arrived. The visible web is a tracing of an invisible one that came first. It is a strange and slightly humbling thought. The universe we can see, the universe of light and color and stars, is in some sense secondary. It is a response, a consequence. The primary structure, the foundational architecture of the cosmos, is made of something we cannot detect directly and do not fully understand. We are, in a sense, reading the shadows cast by something we cannot look at directly, and from those shadows, reconstructing the shape of the thing that cast them. And that reconstruction has been done beautifully and ingeniously through one of the most elegant phenomena in all of astronomy. It is called gravitational lensing, and it is both a practical tool and a kind of poetry. Here is how it works. Einstein's general theory of relativity tells us that mass curves space. The more massive an object, the more it warps the fabric of space-time around it. And light, as it travels through space, follows the curves of that warped fabric. When light passes close to a very massive object, its path is bent, deflected, curved by the gravity of that object in exactly the way that light is bent when it passes through a glass lens. The massive object acts as a lens, bending and focusing the light that passes near it. Now, suppose there is a massive cluster of dark matter between us and a distant galaxy. The dark matter is invisible to us, but its gravity is not. As the light from that distant galaxy travels toward our telescopes, it passes through the gravitational field of the dark matter, and its path is bent. The image of the distant galaxy that we see is distorted, stretched, sometimes split into multiple images, sometimes smeared into arcs of light around the dark matter concentration. The invisible dark matter has revealed itself by what it does to the light passing through it. By studying these distortions carefully, by mapping where light is bent and by how much and in which direction, astronomers can reconstruct the distribution of mass that caused the bending. They can essentially weigh the dark matter. They can trace its outlines. They can map its location in 3 dimensions with remarkable precision. The result is a kind of X-ray of the invisible scaffolding of the universe, an image of the dark architecture built from the bent light of galaxies far beyond it. The images produced by gravitational lensing are among the most beautiful in all of astronomy. Great arcs of light curving around dark central concentrations. Galaxies whose images have been stretched and multiplied by the invisible mass between them and us. Rings of light, called Einstein rings, formed when a distant source, a massive lens, and our telescopes happen to line up perfectly, creating a complete circle of bent light in the sky. Every one of these beautiful distortions is a message written by dark matter in the only language it can speak, the language of bent light and curved space. And what all of this mapping, through lensing and through the dynamics of galaxies and through the large-scale structure of the cosmic web, has revealed is a universe in which dark matter is not peripheral. It is not a footnote or a minor correction to an otherwise well-understood picture. It is the foundation. Without dark matter, the very early universe would never have been able to grow the structures we see today. The tiny density variations that were present after the Big Bang would not have been sufficient, on their own, to draw ordinary matter together fast enough to build galaxies and clusters within the age of the universe. Dark matter, which does not interact with light and therefore was not held back by the pressure of radiation in the early universe, began clumping under its own gravity much earlier. It built the gravitational wells first, and then ordinary matter, freed from the pressure of radiation as the universe cooled, fell into those pre-existing wells and formed the structures we see. Without dark matter, the calculations are unambiguous. The universe would be a featureless, slowly expanding cloud of gas. No galaxies, no stars, no planets, no anything built from ordinary matter, at least not on the scales and in the time frames that have actually occurred. The existence of everything we can see, every star that has ever shone, every world that has ever turned around a star, is contingent on the prior existence of this invisible, mysterious substance that we have never directly detected and do not fully understand. You exist because of dark matter. Take a moment with that thought. Not in any mystical or metaphorical sense, but in the plain, literal, scientific sense. The atoms in your body were forged in stars. Those stars formed in galaxies. Those galaxies formed in dark matter halos. Those halos formed along dark matter filaments. And those filaments formed from the initial clumping of dark matter in the early universe, clumping that was the essential first step in a chain of events that ended billions of years later, with a world and life on it, and you resting quietly in this moment. Deep inside the dark matter filaments, in the densest concentrations where ordinary gas has followed the dark matter's gravitational invitation and pooled and cooled and thickened, something luminous and lovely happens. The gas condenses further. It fragments. And within those fragments, under the weight of their own gravity, the temperature and pressure rise until the conditions become right for nuclear fusion, and a new star ignites. Quietly, in the deep interior of a dark matter filament, light is born. Another small lamp lit in the darkness of the cosmic web, another tiny beacon joining the slow illumination of a universe that began in the dark. This is happening right now. Not in any dramatic or sudden way, but in the slow, patient manner of cosmic processes. Stars are being born at this moment in filaments of dark matter threaded across the universe, tiny ignitions scattered along invisible rivers of a substance we cannot name precisely or detect directly, each one a small victory of complexity over emptiness, warmth over cold, light over dark. And while all of this is happening, while stars are being born and galaxies are spinning inside their dark matter halos and the cosmic web is continuing its slow development, there is another force at work. The universe is expanding. It has been expanding since the Big Bang, and in recent cosmic time, that expansion has been accelerating, driven by what we call dark energy, a separate mystery for another chapter. But this expansion is relevant here because it works, in some sense, against dark matter. Dark matter's gravity pulls. It draws things together. It holds structures in place. It resists the dispersing tendency of the universe's expansion. And so there is a quiet war being fought on timescales so vast that 1,000,000 years is barely a skirmish, between the expansive tendency of the universe and the contracting, binding, holding gravity of dark matter. The structures we see, the galaxies and clusters and filaments that exist today, are the current state of that long, slow battle. Dark matter has managed, so far, in the regions that have had enough density to hold things together against the pull of expansion, to build islands of structure in an expanding sea. But the war is not won. Over the very longest timescales, over time frames so remote that they make the current age of the universe look like a morning, the expansion will continue, and the filaments that are not already gravitationally bound will be stretched and thinned and eventually lost to the growing distances between things. The cosmic web, this grand architecture assembled so patiently over 13 billion years, will eventually, on timescales of trillions of years, be pulled apart by the very expansion of the universe it has always lived within. But that is enormously far away in time. For now, in this moment, in this age of the universe that happens to be the one in which we exist, the dark matter holds. The halos persist. The filaments carry their rivers of invisible substance. The galaxies spin, held together by their dark matter embraces, cradled in the gentle, firm, invisible arms of something we cannot see or name fully or understand completely, and yet something that has made everything possible. Let yourself drift now with that image. The universe, most of it invisible. The scaffolding beneath the cosmic web made of something that passes through light without a word. The galaxies held in their invisible halos, spinning safely inside gravitational cradles assembled from a substance that has no color, no texture, no smell, no light. And yet, profoundly present, profoundly consequential. The most important structural material in the history of the universe, present everywhere and seen nowhere. There is something almost meditative in that idea. The most important things are sometimes the ones you cannot see directly. The foundations of the most impressive structures are often hidden beneath them, invisible, unremarked upon, taken for granted, and yet absolutely essential. The dark matter does not need to be seen to be real. It does not need to be understood to do its work. It has been patiently holding the universe together for over 13 billion years, and it will continue to do so long after every star it helped to birth has burned out and grown cold. In the meantime, there are astronomers, people who have dedicated their lives to this question, who are trying. They are building detectors buried deep underground, shielded from cosmic rays and background radiation, hoping that a particle of dark matter might very rarely, very faintly, interact with ordinary matter in a way that could be measured. They are studying the patterns of the cosmic web in ever finer detail, hoping that the precise distribution of dark matter might reveal clues about its nature. They are thinking and calculating and imagining, following the bent light and the rotating curves and the large-scale structure wherever those trails lead, trying to give a name and a face to the invisible foundation of everything. We do not know yet what they will find. The mystery is still open. The question is still alive. And perhaps that, too, is something to carry with you as you rest tonight. The universe has a secret, the deepest structural secret of all of reality. And it is still a secret. The darkness beneath the cosmic web has not yet revealed its full nature to us. It whispers in the bent light of distant galaxies and in the rotation curves of spinning spirals and in the large-scale patterns of matter across the cosmos. But it has not yet spoken clearly enough for us to understand. For now, let the mystery be enough. Let the darkness be comfortable. Let the invisible scaffolding of the universe hold you, the way it has held galaxies for billions of years, the way it holds the cosmic web in its grand, slow pattern, the way it holds everything together in the face of an ever-expanding void. There is something deeply reassuring about a universe whose foundation, however mysterious, is devoted to holding things together. Rest now. The dark matter is there, even here, even in this room, passing through everything around you as it has always done, quietly, invisibly, without any need for acknowledgement. The most essential invisible thing in the universe, present in the darkness with you, as patient and as vast as the cosmos itself. And in the silence, you are held. Chapter 3: The Great Emptiness. Let your breathing find its own rhythm now. There is no pace to keep, no destination to reach. Simply breathe, and let the air move through you slowly, the way a gentle current moves through a vast and quiet space. Let the weight of the day, whatever it carried, dissolve a little more with each breath out. You are here. You are still. And the universe, as always, is waiting to be explored. We have traveled together through the cosmic web, tracing its great glowing filaments and the galaxies that cling to them. We have descended into the invisible foundations, the dark matter scaffolding that holds the whole luminous architecture in place. And now we turn our attention to something different. Something that is not a structure in the way we usually think of structures. Something defined not by what it contains, but by what it does not contain. We are going to spend some time tonight in the great emptiness. In the silent spaces between the glowing threads of the cosmic web. In regions of the universe so vast and so quiet and so profoundly devoid of stars and galaxies that they have a beauty of their own. A kind of breathtaking, austere beauty that is very different from the sparkling complexity of the filaments, but no less extraordinary for that. These spaces are called cosmic voids. And they are, in their own way, just as remarkable as anything else the universe has to show us. You will remember from our earlier wandering through the cosmic web that between the great filaments there are regions of emptiness. Spaces where the web has no threads, where no galaxies cluster, where the brilliant nodes are absent. We noted them and moved on. But tonight, we slow down and look at them directly, because they deserve far more attention than they are usually given. In many ways, the cosmic voids are the least celebrated and least understood large-scale structures in the universe, and yet they occupy more of it than anything else. Here is the first thing to understand about voids, and it is a fact that takes a moment to fully absorb. Cosmic voids are the largest single structures in the universe by sheer volume. Not the filaments, not the galaxy clusters, not the great walls of galaxies that we will explore in later chapters. The voids, those vast, quiet, empty regions that sit between everything bright and crowded, they are the structures that take up the most space. And they take up an almost incomprehensible amount of it. Estimates suggest that cosmic voids account for roughly 80% of the total volume of the observable universe. 80%. Everything we have discussed so far, every galaxy, every cluster, every filament, every node of the cosmic web, all of the luminous and dark matter that makes up the visible and invisible scaffolding of the cosmos, all of it together fits within the remaining 20% of the universe's volume. The rest, the overwhelming majority of the space that the universe occupies, is void, is emptiness, is the great nothing between the threads. The universe, measured by volume, is mostly empty. Not empty in the sense of a room with the furniture pushed to the walls, but empty in a deeper, more absolute sense. Empty in a way that makes the emptiness of outer space, as we experience it from our solar system, seem positively crowded by comparison. And the shape of these voids is worth picturing. They are not perfectly spherical, though some come close. They tend to be roughly rounded, sometimes described as potato-shaped or bubble-shaped. These irregular rounded forms bounded on all sides by the walls of filaments and sheets of galaxies that define their edges. Imagine great soap bubbles, or the cells of a foam, each one a vast enclosed region of near-nothingness, bounded by thin, bright walls of cosmic structure. The cosmic web, seen from the perspective of the voids rather than the filaments, looks not so much like a web as like a foam. Like the froth on an extraordinary cosmic sea, with the bubbles of emptiness as the dominant feature and the filaments as the thin walls between them. Inside a void, the landscape is almost unimaginably stark. There are almost no galaxies. There is almost no gas, certainly nothing like the density found even in the relatively sparse intergalactic medium of the filaments. There is no starlight to speak of. In the deep interior of a cosmic void, you could be billions of light years from the nearest galaxy cluster, surrounded on all sides by a darkness that has not been touched by the light of a star for millions or billions of years. If you could somehow place yourself inside a void and look around, you would see almost nothing. A handful of very faint, very distant galaxies at the extreme edges of your vision, far away across the boundary walls of the void, and then, in every direction, nothing. Darkness. An emptiness so complete that it would feel, if you could feel it, like the universe had simply forgotten to fill this part of itself. We say almost no galaxies because the voids are not quite absolutely empty, and this is important and rather lovely. The word almost is doing real work in that sentence. The voids do contain something. Not much, but something. Very thin, extraordinarily diffuse clouds of gas drift through the interiors of voids, material so sparse it makes the already gossamer-thin gas of the cosmic filaments seem dense by comparison. And scattered through the voids, rare as islands in the middle of an ocean of ocean, there is the occasional lonely galaxy. But before we meet those solitary wanderers, let us spend a little time with perhaps the most famous void in the known universe. Its name is the Boötes Void, sometimes called the Great Nothing, and it is, by any reasonable measure, one of the most extraordinary places in the observable cosmos. The Boötes Void sits in the direction of the constellation Boötes, which rises in the northern sky during spring and summer evenings and contains the bright star Arcturus, one of the most luminous stars visible to the naked eye from Earth. But far beyond Arcturus, at distances of hundreds of millions of light years, lies this extraordinary region of emptiness. The Boötes Void is nearly 330 million light years across. Let that distance take shape in your mind, slowly. 330 million light years. To cross it, traveling at the speed of light, the fastest speed that anything in the universe can travel, would take 330 million years. That is longer than the time since the Carboniferous period on Earth, when the great coal forests grew and the first reptiles were beginning to appear. It is longer than any time scale that has any meaning to us as creatures of a single lifetime. And it is the distance across just one void, in a universe that contains millions of them. What makes the Boötes Void particularly striking, beyond its sheer scale, is what astronomers found when they first properly surveyed it in the 1980s. They expected, when they pointed their instruments at that region of sky, to find the usual distribution of galaxies, perhaps somewhat fewer than average, but still a reasonable scatter. What they found instead was an almost complete absence. A region of space that, for its size, contained only a tiny handful of galaxies where there should, statistically, have been thousands. The astronomers who discovered it reportedly struggled to believe their own data. An emptiness that large, that thorough, seemed almost to break the rules of what the cosmic web was supposed to look like. One of the astronomers involved in the discovery is said to have remarked, with a kind of odd understatement, that if the Milky Way were situated somewhere in the center of the Boötes Void, we would not have known about the existence of other galaxies until the 1960s. Think about what that means. For most of human history, and in fact for most of scientific history, we did not know that galaxies other than our own existed. It was only in the early 20th century that astronomers established beyond doubt that the fuzzy patches of light visible in long-exposure photographs were not nearby clouds of gas but entire island universes, distant galaxies like our own. If we lived inside the Boötes Void, that discovery would have been delayed by decades, simply because the nearest galaxies would have been so far away, so faint, that our instruments would not have reached them until much more recently. The void is that large, The isolation is that complete. And it is sitting there, right now, in the direction of Boötes, 330 million light-years of darkness, one of the most profoundly empty places in the known universe. And the interior of a void like this is not merely empty of galaxies. It is dark in a way that places near galaxies and clusters are not. In the regions of the cosmic web near bright galaxy clusters, the intergalactic medium is bathed in light, warmed by the radiation of billions of stars, shaped and stirred by the energy output of active galactic nuclei and the explosions of dying stars. There is a kind of ambient luminosity, a background glow of energy, even in the spaces between galaxies in those crowded regions. Inside a void, that glow is absent. The darkness is pure. The cosmic background radiation is there, that ancient whisper of light left over from the Big Bang itself, but the secondary illumination from nearby galaxies, the ultraviolet light, the X-rays, the radio waves produced by active galaxies and star formation, almost none of that reaches the deep interior of a void. It is untouched, pristine. A region of the universe that has been sitting in its quiet dark for billions of years, largely undisturbed by the energetic processes that shape the rest of the cosmos. There is something almost sacred about that kind of stillness. Not in any religious sense, but in the sense that the void interiors are among the least altered places in the universe. While the filaments and the galaxy clusters have been in constant dynamic activity, stars forming and dying, galaxies merging and colliding, gas being heated and shocked and enriched with heavy elements, the void interiors have been quietly expanding, growing slowly larger, untouched by most of what we think of as the activity of the universe. And that expansion is worth dwelling on, because it is one of the most fascinating and somewhat counterintuitive things about cosmic voids. The universe as a whole is expanding. Every region of space is, on average, growing larger over time as the universe continues on the course it set at the Big Bang. But this expansion is not uniform everywhere. In regions of high density, in galaxy clusters and along filaments, the local gravity of all that matter partially counteracts the expansion, slowing it down. The matter is dense enough, its gravitational pull strong enough, to resist the universe's tendency to pull everything apart. In the voids, there is almost no such resistance. There is almost no matter, and therefore almost no local gravity to push back against the expansion. And so the expansion inside a void proceeds faster than the cosmic average. The void interiors are regions where the universe's expansion is least opposed, where it runs most freely, where space itself is stretching most rapidly relative to the surrounding structures. The consequence of this is that voids are growing. Over billions of years, the voids are becoming larger. The expansion within them is pushing the walls of the void, the surrounding filaments and galaxy sheets, slowly further apart. The bubbles in the cosmic foam are inflating, and as they inflate, they push the material in the walls into thinner, more concentrated sheets and filaments. The cosmic web is, in this sense, being sculpted by the growth of the voids from the inside. The emptiness is shaping the structure of everything around it by expanding and pressing outward, concentrating matter into the web-like patterns we observe. It is a remarkable dynamic. The voids do not simply sit passively inside the structure of the cosmic web. They actively participate in shaping it. They are not the absence of structure. They are a kind of structure in their own right, one defined by expansion rather than concentration, by emptiness rather than density, but no less dynamically important for that. Now, let us return to those rare, lonely inhabitants of the voids. Because even in the great emptiness, Even in regions where the density of matter is hundreds of times lower than average, there are occasionally galaxies. Not many, a handful scattered through a volume that might contain thousands in a denser region. But they are there, and they are fascinating. These are called void galaxies, and they are among the strangest and most quietly beautiful objects in the universe, simply because of where they find themselves. A void galaxy is a galaxy that has somehow ended up in the interior of a cosmic void, far from the great filaments and clusters, surrounded on all sides by hundreds of millions of light-years of near-nothing. It is, as galaxies go, profoundly alone, and that solitude shapes what a void galaxy is like. In a galaxy cluster or along a crowded filament, galaxies are not simply passive inhabitants of space. They interact with each other. They distort each other's shapes with their gravitational pulls. They collide and merge, combining their star populations and their gas reservoirs into new, transformed objects. The tidal forces of neighboring galaxies strip material from the outer edges of each other. Close encounters trigger bursts of star formation. The environment of a crowded galaxy cluster is a dynamic, chaotic, constantly churning place, and the galaxies within it bear the marks of that turbulent history. A void galaxy has none of that history. It has evolved in isolation, far from any gravitational partner, undisturbed by the tug-of-war that characterizes life in a cluster. The result is a galaxy that is, in some sense, purer, less altered from its original form. Void galaxies tend to be bluer than their cluster counterparts, a sign that they are still actively forming stars from their gas reservoirs, gas that in a cluster would long since have been stripped away or heated beyond the point where it could cool and collapse into new stars. They tend to be more regular in shape, less distorted by gravitational interactions. They are quieter, simpler, more pristine. There is something touching about a void galaxy. Imagine it sitting there in the dark, hundreds of millions of light-years from the nearest galaxy cluster, its stars burning steadily, its gas clouds slowly producing new generations of stars, entirely unaware, if we can use such a word for a galaxy, of the grand drama being played out in the filaments and clusters far beyond it. It has simply been doing what galaxies do, slowly and quietly, without interruption, without neighbor, without the upheavals of collision or the stripping violence of a cluster environment. Just drifting in the immensity of the void, evolving at its own pace in its own enormous silence. And our own galaxy, the Milky Way, has a relationship with all of this that is worth considering as you rest tonight. We are not inside a void in the deep sense that some void galaxies are. We are not in a particularly dense region either. We find ourselves, as is perhaps appropriate, somewhere in the middle. The Milky Way and its small cluster of neighboring galaxies, a collection called the Local Group, are situated near the edge of a relatively empty region of the universe known as the local void. The local void is not as empty or as vast as the Boötes void. It is a more modest example, a region of below-average galaxy density extending across tens of millions of light-years in certain directions from us. And we are near its edge, in the sense that the Great Virgo Supercluster and the broader Laniakea Supercluster, which we will explore in a later chapter, lie in another direction. We are, in a sense, perched on the rim of a great empty basin, with the crowded richness of the local supercluster in one direction and the deep quiet of the local void stretching away in another. This position is not without consequence. The local void, like all voids, is expanding, and that expansion exerts a gentle but measurable push on the local group, nudging us slowly in the direction away from the void and toward the great attractor regions that lie in the other direction. Even our motion through the universe, the direction in which the Milky Way and its companions are drifting on the largest scales, is partly shaped by the gentle outward pressure of the void behind us. We are being pushed by emptiness, gently, slowly, across timescales too vast for any human observation to directly measure. But the void is there, and its expansion is real, and it is one of the forces, alongside the gravity of distant superclusters, that determines where we are going in the grand flow of the cosmos. As you lie in the quiet now, let yourself imagine the emptiness of the voids, not as a frightening or desolate thing, but as a kind of profound peace. The deep interior of a cosmic void is perhaps the most undisturbed place in the universe. No star explosions, no galaxy collisions, no fierce radiation from active galactic cores. Just the slow expansion of space itself, unhurried, undramatic, stretching in every direction. The ancient whisper of the cosmic microwave background washing through it like the memory of a sound. And very occasionally, perhaps once every 100 million light years or so, a single quiet galaxy evolving slowly in the dark, doing its patient, ancient work. There is a kind of peace in that image. The great emptiness of the voids is not a failure or an absence in any meaningful sense. It is a fundamental feature of the universe's architecture, as essential to the whole as the bright and crowded filaments. Without the voids expanding and pushing, the filaments would not be as concentrated or as defined as they are. Without the voids, there would be no web, just a more uniform, less structured distribution of matter, and a universe far less interesting than the one we inhabit. The emptiness makes the structure possible. The silence gives shape to the sound. The dark gives the light somewhere to be. Rest quietly with the voids tonight, with the thought of all that dark, patient, pristine space, expanding slowly in every direction, untouched for billions of years, waiting in its enormous quiet while the universe goes about its business in the thin, bright threads around it. 80% of the universe's volume is this: deep, clean, empty, expanding, peaceful dark. And you are here on a small world, near the edge of one of those quiet regions, held gently between the emptiness of the local void and the rich complexity of the supercluster beyond, between the silence and the sound, between the great nothing and the great something. It is a good place to rest. Let the emptiness be comfortable. Let the vast, quiet dark of the cosmic voids be a companion tonight rather than an absence. Let yourself spread out into the stillness of it, the way the void itself spreads through the universe, gently, without resistance, taking up whatever space is given to it. There is nowhere you need to be. There is nothing pressing in from any direction. Just the slow, quiet expansion of a peaceful dark, and you resting inside it, breathing, letting go, drifting gently into sleep. Chapter 4. The Crowded Cities. Breathe in slowly, and breathe out. Let your body be heavy. Let your thoughts be light. There is nothing to hold on to right now, and nothing that needs holding. Simply be here, in this comfortable dark, and let the universe come to you. We have traveled a long way together through these chapters. We have traced the grand architecture of the cosmic web, followed the invisible rivers of dark matter that give it its shape, and rested for a while in the extraordinary silence of the cosmic voids. We have seen the universe at its emptiest. We have felt the quiet of those vast, dark, expanding spaces between the filaments, and we have let that quiet settle into us. Tonight, we move in the opposite direction. We leave the silence of the voids and travel toward the brightest, most crowded, most energetic places in the large-scale structure of the universe. We are going to visit the galaxy clusters, the great cosmic cities, the places where gravity has done its most spectacular and concentrated work, where hundreds or thousands of galaxies have been drawn together into immense, gravitationally bound communities, each one burning with the light of billions and billions of stars. If the voids are the deserts of the universe, wide and quiet and undisturbed, then the galaxy clusters are its cities, its great, dense, teeming metropolises, where everything is happening at once, where the energy is intense and the activity never really stops, where galaxies that might otherwise have drifted peacefully alone in the cosmos are instead crowded together in a shared gravitational embrace, interacting and influencing one another across the billions of years of their shared existence. A galaxy cluster is, at its most basic, a collection of galaxies held together by gravity. Not the gravity of any single object, but the combined gravitational pull of all the galaxies together, all the dark matter in which they are embedded, and all the hot gas that fills the spaces between them. A cluster is a system, a community, an entity that is in some meaningful sense more than just the sum of its parts, because the parts are so deeply intertwined, so profoundly affecting one another, that the cluster as a whole behaves as a single, enormous gravitational object. A single galaxy cluster can contain anywhere from a few hundred to several thousand individual galaxies. Not star systems, not single stars. Entire galaxies, each one potentially containing hundreds of billions of stars, each one spanning tens or hundreds of thousands of light years, gathered together in a region of space that, while vast by any ordinary reckoning, is tiny compared to the intergalactic distances we have been contemplating. A cluster might span only a few million light years across, but within that volume, the density of galaxies is hundreds or thousands of times higher than the cosmic average. And the spaces between those galaxies, the regions within the cluster that are not occupied by the galaxies themselves, are not empty, not remotely. While the vast intergalactic spaces of the cosmic voids are almost perfectly empty, the intracluster medium, the space between galaxies within a cluster, is filled with a thin but extraordinarily hot plasma. This is gas that has been heated to temperatures of tens of millions of degrees by the processes of cluster formation, by the shocks of matter falling into the cluster's gravitational well over billions of years, by the explosive energy output of the massive black holes at the centers of the cluster's galaxies. This plasma is so hot that it glows not in visible light but in X-rays, the high-energy radiation produced by matter at such extreme temperatures. If you could see X-rays the way we see visible light, a galaxy cluster would appear as a great soft glow, an enormous luminous cloud of superheated gas surrounding the individual galaxies like an atmosphere surrounding a planet, but at scales millions of times larger. The galaxies would be embedded in this glowing cloud, swimming through it, occasionally disturbing it with their motions or their energetic nuclei, while the cloud itself slowly radiates energy into the surrounding void. This intracluster gas is actually one of the ways we study galaxy clusters in detail. X-ray telescopes in space, Instruments designed specifically to detect the high-energy light that cannot penetrate Earth's atmosphere have mapped the distribution of this hot gas in clusters across the universe. The maps they produce are stunning, revealing the complex, sometimes disturbed, sometimes beautifully regular structure of these great collections of galaxies in a light that the human eye never evolved to see. But let us begin close to home, because we do not need to travel to distant, exotic clusters to find a galaxy cluster. We are already inside one, or rather, we are inside something adjacent to one, something connected to one, something that is being slowly, gently, inexorably drawn toward one. Our galaxy, the Milky Way, is part of a small collection of galaxies called the local group. Small, in this context, means a few dozen galaxies within a region of space perhaps 10 million light-years across. By cosmic standards, the local group is a modest gathering, not a grand cluster, but something more like a small town or a village compared to the great cities of the more massive clusters. There are about 54 known members of the local group, though the count shifts as new small dwarf galaxies are discovered hiding in the dark. The local group has two dominant members, two large spiral galaxies that together account for the vast majority of its total mass and luminosity. One of them is us. The Milky Way, that great barred spiral of a few 100 billion stars that constitutes our home in the cosmos. And the other, our largest and most massive neighbor, is the Andromeda Galaxy. Andromeda sits at a distance of about 2.5 million light-years from us, which sounds enormous, and by everyday standards it is. But in the context of cosmic distances, it is our nearest large neighbor, close enough that on a very dark night, far from city lights, you can see it with the naked eye as a faint, elongated smudge of light in the constellation Andromeda. That smudge, that soft blur visible to the unaided human eye, is an entire galaxy of roughly 1 trillion stars. It is the most distant thing the human eye can see without optical aid, and it is heading toward us. Andromeda and the Milky Way are gravitationally bound to each other, and over billions of years they have been drawing closer. In about 4.5 billion years, in a span of time longer than the entire current age of the Earth, the two galaxies will collide. Not in the explosive, violent way that the word collision suggests when applied to ordinary objects, but in the slow, majestic, gravitational way that galaxy collisions happen. Over hundreds of millions of years, the two great spirals will interpenetrate, their stars sweeping past each other with almost no physical contact, since stars are so small relative to the distances between them. But the gravitational effects will be profound and spectacular. Tidal forces will draw long streamers of stars out into space. The disks of both galaxies will be distorted, warped, flung into new configurations. And eventually, over billions of years, the two galaxies will merge into a single, larger, probably elliptical galaxy, a new and transformed object that astronomers have already given a provisional name, Milkomeda. That future collision and merger is worth contemplating not as something to worry about, but as a reminder of how dynamic the universe truly is, even on scales that seem permanent and fixed to us. The night sky that has looked essentially the same to every human who has ever lived under it will, in a cosmically brief span of future time, be transformed beyond recognition. The Milky Way we belong to is not a permanent fixture. It is a participant in an ongoing gravitational story, And the next chapter of that story is already being written by the slow approach of Andromeda across 2.5 million light-years of space. Around us and Andromeda, the rest of the local group's 50-odd galaxies orbit and drift. Most of them are dwarf galaxies, small irregular or elliptical collections of stars, far less grand than the two dominant spirals but no less real, each one a community of millions or billions of stars following its own slow path through the gravitational landscape of the group. Some of them, like the Magellanic Clouds, are close enough to be visible from the southern hemisphere as faint patches of light, satellites of the Milky Way being gently pulled along with us through the universe. But the local group, our small cosmic village, does not exist in isolation. Beyond its boundaries, at a distance of about 65 million light-years, lies the Virgo cluster. And the Virgo cluster is something of a different order of magnitude entirely. The Virgo cluster is a massive gathering of more than 1,000 galaxies, concentrated in a region of space a few tens of millions of light-years across. It is the nearest large galaxy cluster to us, the heart of the broader Virgo supercluster in which our own local group resides as an outlying member. Where our local group is a village, the Virgo cluster is a great city, dense and energetic and dominated by some of the largest and most massive galaxies in our cosmic neighborhood. At the center of the Virgo cluster sits a galaxy called Messier 87, also known as M87. It is one of the largest known galaxies in the local universe, a vast elliptical galaxy containing an estimated several trillion stars, orders of magnitude more massive than our Milky Way. At its center, M87 harbors one of the most massive black holes known, a gravitational monster billions of times more massive than our Sun, which made history in 2019 when it became the first black hole ever to be directly imaged. The famous photograph of that great glowing ring of superheated matter surrounding a region of absolute darkness, the event horizon of the black hole itself, came from M87, sitting at the heart of the Virgo cluster 65 million light-years away. And the Virgo cluster is so massive, so gravitationally powerful, that its influence extends far beyond its own boundaries. The combined gravity of all those thousands of galaxies, all that dark matter and hot intracluster gas, creates a gravitational pull that reaches across tens of millions of light-years in every direction, including in our direction. The Virgo cluster is slowly, gently, but measurably pulling our entire local group toward it. Not fast enough to be detectable over a human lifetime, not fast enough to be seen directly, but present and real in the data, a steady gravitational current flowing from us toward Virgo, carrying our local neighborhood along with it across cosmic time. We are falling very slowly toward the city, drawn by its gravity, flowing along the gentle current of its attraction, the way a river flows toward the sea. It will take billions of years, and the details of what happens when we arrive depend on many factors that are difficult to predict with precision. But the pull is there, and it is real. Beyond the Virgo cluster, the structure of the universe on even larger scales reveals something even more extraordinary. Galaxy clusters, for all their grandeur, are not the largest gravitationally significant structures in the cosmos. When clusters themselves group together, when multiple clusters and their surrounding galaxies gather in a broader region, the result is something called a supercluster. And superclusters are among the most impressive things the universe has built. A supercluster can span hundreds of millions of light-years and contain tens of thousands of galaxies distributed across dozens of individual clusters. The Virgo supercluster, sometimes called the local supercluster, of which we are a peripheral member, extends across roughly 110 million light-years and contains perhaps 100 galaxy groups and clusters, including the Virgo cluster at its center and our own local group at its edge. But superclusters are fundamentally different from clusters in one important way. A galaxy cluster is gravitationally bound. Its member galaxies are trapped by the shared gravity of the cluster, unable to escape, destined to remain part of the cluster for the rest of cosmic time. A supercluster is not, at least not entirely. The individual clusters within a supercluster are not all gravitationally bound to the supercluster as a whole. They are close enough to be part of a loose association, to share the same broad region of the cosmic web, to influence each other's motions. But the expansion of the universe is pulling them apart, and in the very long run, the supercluster will not remain a coherent structure the way a cluster will. The individual clusters will drift further apart as the universe expands, and in the deepest future, they will be separated by distances so vast that the light from one cluster will no longer reach another. Superclusters are therefore transitional structures, associations rather than permanently bound communities, living at the boundary between the gravitationally dominated world of clusters and the expansion-dominated world of the largest cosmic scales. They mark the nodes and filaments of the cosmic web, the bright intersections where multiple threads come together and the density of matter is highest. Within superclusters, in the crowded environments where clusters are relatively close and galaxies are meeting and passing and sometimes colliding, the lives of individual galaxies are shaped by their environment in profound ways. Galaxy collisions and mergers happen in slow, magnificent, billions of years-long dances. When two galaxies approach each other closely enough, their mutual gravity begins to distort their shapes. Long tidal tails of stars are drawn out. Gas is compressed and star formation accelerates in brilliant bursts. The galaxies might sweep past each other in a first encounter, only to be brought back by gravity for a second, closer pass. And eventually, if the conditions are right, they merge. Two spiral galaxies become one larger, often elliptical galaxy. Their stars mix together in a new configuration, their gas largely consumed in the star formation triggered by the encounter. This process of collision and merger is one of the primary ways that the largest galaxies in the universe have become as large as they are. The great elliptical galaxies at the centers of rich clusters, galaxies like M87, have grown to their extraordinary sizes through a long history of mergers and cannibalism, absorbing smaller galaxies that wandered too close, incorporating their stars and gas, growing ever larger and more massive over billions of years of cosmic time. Now, beyond the Virgo supercluster, further out in the universe, lies one of the most impressive and somewhat dramatic concentrations of matter in our cosmic neighborhood. It is called the Shapley Supercluster, and it is something genuinely remarkable. The Shapley Supercluster is located about 650 million light-years away from us, in the direction of the constellation Centaurus. It is one of the largest and most massive concentrations of galaxies in the observable universe. A supercluster of superclusters, a region where the density of matter is dramatically higher than the cosmic average, home to dozens of rich galaxy clusters and tens of thousands of individual galaxies crowded together across a region hundreds of millions of light-years across. The Shapley Supercluster is so massive, its gravitational pull so immense, that it is influencing the motions of galaxies across an extraordinary volume of space, including our own. When astronomers measure the motion of our galaxy, the Milky Way, through the cosmos, they find that we are not simply drifting with the general expansion of the universe. We have what is called a peculiar velocity, a motion relative to the cosmic average, and that motion is directed partly toward the Shapley Supercluster, 650 million light-years away. The gravity of that great distant concentration of galaxies is pulling on us, drawing us toward it along with thousands of other galaxies in our broader cosmic neighborhood, like a great river of matter flowing toward an ocean. It is a remarkable thing to contemplate. The Milky Way, our home, the galaxy that contains every star you have ever seen in the night sky and every world that any human being has ever stood upon, is being carried through the universe by gravitational currents that originate hundreds of millions of light-years away. We are part of flows and structures that operate on scales so vast they make our galaxy look like a single drop in a great cosmic river. We are not simply here. We are going somewhere, drawn by the gravity of the universe's largest gatherings, part of a pattern and a flow that has been operating since long before our solar system existed. And all of this, the clusters and the superclusters, the great gravitational cities and the slow rivers of galaxies flowing toward them, all of it is organized along the filaments and nodes of the cosmic web we began with. The superclusters mark the brightest nodes, the great intersections where multiple filaments converge and matter has accumulated most densely over the longest spans of time. The clusters are concentrated within those nodes, the galaxies gathered most thickly where the dark matter scaffolding has drawn matter most powerfully together. The cosmic web, the dark matter, the voids, the clusters, the superclusters, all the structures we have been exploring together are not separate things. They are one thing, one interconnected system, one grand architecture, one universe working through the same basic processes of gravity and expansion and time, from the smallest galaxy cluster to the largest supercluster, from the quantum ripples of the very early universe to the great rivers of galaxies flowing toward the Shapley Supercluster today. It is all one story, a single, unbroken narrative of matter and gravity and time, playing out across scales that span a factor of billions from the smallest detail to the largest structure. Rest with that now. The city lights of the galaxy clusters burning in the dark of the cosmic web. The great M87 at the heart of Virgo, with its ancient black hole and its trillions of stars. The Andromeda Galaxy approaching us across 2.5 million light-years in a slow dance that will take billions of years to complete. The Shapley Supercluster far beyond, drawing us toward it with its immense and patient gravity. The local group, our small village, drifting gently in the gravitational currents of a universe far vaster than any single mind can hold. You are part of all of it. You are in the local group, orbiting in the Milky Way, orbiting in our solar system, resting on this small world, breathing slowly in the quiet. And beyond the walls of wherever you are resting, the universe continues its great, slow, gravitational dance. Galaxies are merging in slow-motion collisions hundreds of millions of light-years away. Gas is being heated to tens of millions of degrees in the hearts of clusters. Black holes are growing. Stars are being born. And the great clusters and superclusters are drawing matter toward them along the filaments of the web, as they have been doing for billions of years and will continue to do for billions more. None of that requires anything of you tonight. The universe is doing all of it on its own, as it always has. You can simply rest here, one small warm creature on one small world, and let the grand mechanics of the cosmos go on without your help. The clusters will hold. The gravity will persist. The great cities of the universe will continue their glowing, energetic existence far beyond our sight and far beyond our time. And you can sleep quietly, held by the gravity of your own small world, while the rest of it goes on around you in the beautiful, incomprehensible, patient dark. Chapter 5. Lania, our immeasurable heaven. Let your eyes be closed, or nearly so. Let the room around you grow quiet in your awareness, the way a shoreline grows quiet when you stop listening to the individual waves and simply hear the whole ocean at once. You are comfortable. You are still. And there is something waiting to be told tonight that is, among everything we have explored so far, perhaps the most personally meaningful of all. Because tonight we are going to find out where we live. Not the street, not the city, not the country, not the planet. We know those. Tonight we are going to understand our address in the cosmos at its largest scale. We are going to discover the superstructure that is our true home in the universe, the vast and beautiful system that contains everything we have discussed in every chapter before this one. The Milky Way, the local group, the Virgo cluster, all of it, nested inside something so grand and so recently discovered that the people who found it chose to give it a name worthy of its scale. They called it Laniakea. Say that word quietly to yourself if you like. Laniakea. It comes from the Hawaiian language, and it is a word that carries a great deal of meaning in very few syllables. Lani in Hawaiian means heaven or sky. The Kea means immense or spacious or without boundaries. Together, they form a word that translates, roughly, as immeasurable heaven or immense sky. A name that gestures towards something so vast that the usual measures do not apply. The astronomers who named it chose well, because Laniakea is, by any reasonable definition, immeasurable. Or rather, we can measure it, but the measurements are so large that they resist any intuitive understanding and must simply be held lightly in the mind, like the memory of a dream. The story of Laniakea's discovery begins in 2014, which in the long history of astronomical discovery is extraordinarily recent. For most of the history of our understanding of the large-scale structure of the universe, astronomers knew that galaxies were grouped into clusters, and that clusters were associated in broader superclusters, but the boundaries of those superclusters were poorly defined. Where did one supercluster end and another begin? The question turned out to be harder than it sounds, because superclusters do not have sharp edges the way a cluster does. They blend into the surrounding structure of the cosmic web, and identifying them required a new way of thinking about what defines a supercluster. The breakthrough came from a team of astronomers who decided to approach the question differently. Rather than simply looking at where the galaxies are, they looked at how the galaxies are moving. Every galaxy in the universe has a velocity, a direction, and a speed at which it is traveling through space. Some of that velocity comes from the overall expansion of the universe, the cosmic tide that carries everything apart. But galaxies also have what are called peculiar velocities, motions relative to the cosmic average that are driven by local gravity, by the pull of nearby concentrations of matter. The insight the team had was this: if you can map the peculiar velocities of thousands of galaxies, you can trace the gravitational landscape they are responding to. Galaxies flow toward concentrations of mass the way water flows downhill. By following those flows, by tracing where the gravitational currents lead, you can map the watersheds of the universe, the regions within which all the gravitational flow converges toward the same central basin. And when they did this, when they mapped the flow patterns of galaxies across a vast region of space, what they found was extraordinary. They found that our local group and the Virgo cluster and thousands of other galaxy groups and clusters across an enormous volume of space were all part of the same gravitational watershed, all flowing gently toward the same central region, all part of the same immense superstructure. A superstructure that had been surrounding us for the entirety of our existence without any of us knowing it was there. That superstructure is Laniakea, and its dimensions are, as promised, difficult to hold in the mind. Laniakea spans approximately 520 million light-years in diameter. 520 million light-years. We have spoken of large distances in every chapter of this journey, but it is worth pausing here. The distance to the nearest star beyond our Sun is about 4 light-years. The diameter of the Milky Way is about 100,000 light-years. The distance to the Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years. And Laniakea, the supercluster that contains all of those things, is 520 million light-years across. It is 200 times wider than the distance to Andromeda. It is 5,000 times wider than the Milky Way itself. It is an object so large that light, traveling at the ultimate speed limit of the universe, would take 500 million years to cross it. Within that volume, Laniakea contains approximately 100,000 individual galaxies. 100,000, each one a system of billions or hundreds of billions of stars. Each one a world unto itself, a vast community of suns and planets and gas and dust, orbiting and evolving across billions of years. All of them, every single one, part of this single superstructure that we call our cosmic home. And the mass of all of that, the galaxies, the gas, the dark matter that pervades and holds the whole structure, adds up to something almost beyond imagining. Laniakea contains the mass equivalent of roughly 100 million billion suns. 100 million billion. Written out, that is a 1 followed by 17 zeros. It is the combined mass of 100,000 galaxies, each containing hundreds of billions of stars, plus all the dark matter surrounding them, plus all the hot gas filling the spaces between them. It is the largest thing that we can meaningfully call our home. When the team of astronomers, led by Brent Tully and his colleagues, published their findings and revealed the shape and extent of Laniakea, they also released a visualization, a three-dimensional map of the supercluster showing the positions of its galaxies and, crucially, the flow lines, the paths along which all those galaxies are moving through gravitational space. And that map revealed something beautiful. Laniakea, seen in this way, does not look like a simple blob or a dense cluster. It looks like a leaf, a delicate, branching, luminous leaf stretched across space, with long tendrils and filaments extending outward from a central region, curving and converging toward the heart of the structure. Or perhaps, if you let the image shift slightly, it looks like a watershed seen from above, the way a river system looks when you trace all the tributaries flowing down toward the main channel. The outer branches of Laniakea, the distant galaxy groups at the edges of the supercluster, are like the high ridgelines of a vast watershed, and everything within the watershed flows, along its own gentle gravitational stream, toward the center. And at that center, at the gravitational heart of Laniakea, toward which all 100,000 member galaxies are slowly flowing, there is something extraordinary, something mysterious. something that sits at the core of one of the most compelling and enduring puzzles in modern astronomy. It is called the Great Attractor. The Great Attractor is a name that carries a certain drama, and perhaps appropriately so. It refers to a region of space located roughly 150 to 250 million light-years away from us, in the direction of the southern sky, toward the constellations of Centaurus and Norma. It is a region where the density of matter is exceptionally high, where the combined gravity of multiple massive galaxy clusters and their associated dark matter creates a gravitational well so deep and so powerful that it draws everything in its vicinity toward it, the way a Great Depression in a landscape draws all the water around it downhill. All of the galaxies within Laniakea, including our own Milky Way and the entire local group, are flowing toward the Great Attractor. We are moving through space, right now, at a speed of roughly 600 kilometers per second in the direction of the Great Attractor. That is about 370 miles per second. It sounds fast, and by human standards it is almost unimaginably fast. But the universe is so large that even at that speed, on human timescales, we are essentially stationary. The Great Attractor is so far away that our motion toward it is completely imperceptible on any timescale shorter than millions of years. Still, the journey is real. The motion is real. Right now, as you rest, the Milky Way is being carried through space toward the heart of Laniakea, drawn by the gravity of the Great Attractor at 370 miles per second. A cosmic journey in the dark, patient and silent and ongoing that has been happening for billions of years without any of us noticing. But here is what makes the Great Attractor particularly fascinating and what gives it its air of enduring mystery. We cannot see it. Not easily. Not completely. Not the way we can see the Virgo cluster or the Shapley supercluster or other distant concentrations of mass. The reason is that the Great Attractor lies almost exactly in the plane of the Milky Way's disk, in the direction where our own galaxy's stars and dust and gas are thickest, where the interstellar medium is densest, where the obscuring material between us and distant objects is most effectively blocking our view. Imagine trying to look at something on the far side of a very thick, very dusty fog. You can sense that something is there, you can detect its effects, you can measure the gravitational pull it is exerting on everything around it. But actually seeing it, resolving the details, understanding precisely what is at the center of all that gravitational attraction remains stubbornly difficult. We have been able to partially pierce the obscuring veil using radio telescopes and infrared instruments, which are less affected by dust than visible light telescopes. We have identified a major galaxy cluster called the Norma cluster as one of the primary components of the Great Attractor region. We know the general shape and extent of the concentration, but the full picture remains somewhat veiled, wrapped in the dusty disk of our own galaxy like a secret kept by the very structure we call home. The Great Attractor is there. We are moving toward it, and it is partially hidden from us by the galaxy in which we live. There is something almost poetic in that. The most significant gravitational landmark in our cosmic neighborhood, the focal point of our entire supercluster, hidden behind a curtain of stars and dust belonging to our own Milky Way. It is worth saying something about what the Great Attractor actually is, in physical terms. It is not a single object in the way a black hole or a galaxy is a single object. It is a region, a concentration of mass distributed across millions of light years, made up of multiple galaxy clusters and their associated dark matter, all positioned in the same broad area such that their combined gravity creates the deep attractive well we have been describing. The Norma cluster is one of the major contributors. The broader Centaurus supercluster is part of the story, and the Shapley supercluster, which we mentioned in the previous chapter, lying some distance further in the same general direction, adds its own pull to the overall flow. The great attractor is, in some sense, the gravitational drain in the basin that is Laniakea, the place where the watershed converges, the destination toward which all the gentle gravitational currents of our supercluster are flowing. And whether we will actually reach it, whether the expansion of the universe will eventually overcome the gravitational pull before our cosmic neighborhood completes its long journey, is a question whose answer depends on details of the universe's future that remain genuinely uncertain. Now, returning to Laniakea as a whole, there is a quality to its shape and structure that the visualization makes particularly beautiful. When you look at the flow map, at those curving lines showing the paths along which galaxies are moving through gravitational space, you see something that resembles nothing so much as a great cosmic watershed. The analogy is not merely aesthetic, it is mathematically precise. The team that discovered Laniakea defined it using exactly this concept, identifying the boundaries of the supercluster as the gravitational divides, the ridgelines, where the flow changes direction, where galaxies stop being drawn toward our central attractor and begin being drawn toward a different one. At the edges of Laniakea, the flow of galaxies changes character. Instead of being drawn inward toward the great attractor, galaxies near the boundary are pulled in other directions toward other attractors belonging to other superclusters. In one direction, a neighboring superstructure called the Perseus-Pisces supercluster reaches out its own gravitational tendrils and draws away the galaxies that live closer to its own watershed than to ours. The boundary between Laniakea and Perseus-Pisces is not a sharp line but a gradual transition, a gravitational divide where the competing poles balance and the flow changes allegiance from one vast structure to another. Our position within Laniakea is worth considering. We are not at the center. We are not near the great attractor. We are somewhere toward the outer edges of one of Laniakea's great filamentary arms, a relatively modest position in the outskirts of an enormous structure, like a small town on the far edge of a vast country, a long way from the capital. The local group, our small village of 50-odd galaxies, is flowing along with everything else toward the great attractor, but we are starting that journey from the periphery, a long, long way from home. And even Laniakea, for all its staggering size, for all the grandeur of its 520 million light-year span and its 100,000 galaxies and its 100 million billion solar masses, even Laniakea is not the end of the story. It is not the top of the hierarchy. It is not the largest structure in the universe. It is, as the astronomers who named it pointed out, just one knot in the much larger cosmic web. One node, one watershed among many, one leaf in an infinitely branching tree. The cosmic web contains countless superclusters like Laniakea. Some are comparable in size. Some are larger. The Hercules-Corona Borealis Great Wall, which we may explore in a later chapter, spans billions of light-years and makes Laniakea look modest. The universe is organized in a hierarchy of structures, from planets to stars to galaxies to clusters to superclusters to the filaments and walls of the cosmic web, and each level of that hierarchy contains the levels below it the way a Russian nesting doll contains smaller dolls within smaller dolls, each one a complete structure in itself and yet part of something larger. Laniakea is our level in that hierarchy, our supercluster, our immeasurable heaven, the largest structure that we can meaningfully call home. within which all the addresses that have ever mattered to any human being are nested. Every place that has ever been named, every landscape that has ever been painted or photographed or described, every sky that has ever been looked up into and wondered at, all of it is contained within the flowing, branching, leaf-shaped arms of Laniakea, drifting together toward the great attractor in the patient dark. There is something quietly overwhelming about that, and at the same time something quietly comforting. We are not adrift in a random universe. We have an address. We belong to something. The Milky Way is not just floating in a featureless void, but is part of the local group, which is part of the Virgo Supercluster, which is part of Laniakea, which is part of the cosmic web. We are embedded in structure all the way up, connected to larger and larger things through the language of gravity and the passage of time. There is, if you want it, a kind of belonging in that thought. A sense that the universe has not scattered us randomly but placed us within a pattern so large and so beautiful that it took us until 2014 to see it. Let yourself settle into the name now. Laniakea, immeasurable heaven, our cosmic home. 520 million light-years of structure, 100,000 galaxies flowing in gentle gravitational currents toward a distant, partially hidden center. A great leaf of light spread across the darkness. A watershed of the universe, with our small galaxy moving slowly toward its heart. You are inside this. Right now, as you breathe and let yourself drift toward sleep, you are inside Laniakea. The walls of the room around you, the bed or couch or floor beneath you, the sky above the roof, the stars beyond the sky, the Milky Way beyond the stars, and all of it, all the way out to the outermost tendrils of the supercluster, flowing together, slowly, toward the great attractor in the dark. The Hawaiian language, from which Laniakea's name comes, is one of the world's great languages of the sea and sky, a language developed by people who navigated the open Pacific by the stars, who knew the sky intimately and trusted it to guide them home. There is something fitting about the fact that the name for our cosmic home, our true address in the universe at its grandest scale, comes from people who understood, better than most, what it means to navigate by the stars. To look up and see not just light but direction. Not just distance but belonging. Not just the universe but home. Let the immeasurable heaven hold you tonight. Let the knowledge that you are inside it, that you have always been inside it, that every person who ever lived was inside it without knowing its name, be a comfort rather than a weight. The universe is not empty and cold and indifferent. It is full and patterned and organized on scales we are only just beginning to understand, and somewhere in the middle of all of it, in the outer reaches of a flowing, branching supercluster with a beautiful name, there is a small blue world, and on it, you resting, breathing, safe, and home. Sleep now. The currents of Laniakea will carry you gently, as they have always done, while the universe goes on being immeasurable and beautiful around you. Chapter 6. The Titans of the Cosmos. You have come such a long way tonight. Through all of these chapters, through all the quiet hours of this journey, you have traveled further than any spacecraft ever built, further than any light that has left our galaxy in a human lifetime, further than almost any distance the human mind has ever genuinely tried to hold. You began with the cosmic web, those great glowing filaments stretching across the universe like threads of luminous silk. You descended into the invisible scaffolding of dark matter, the foundation beneath the foundation. You rested in the profound silence of the cosmic voids, those vast and pristine emptinesses that make up most of the universe's volume. You visited the great galaxy clusters, the crowded, brilliant, energetic cities of the cosmos. And in the last chapter, you found your true address, your place in the immeasurable heaven of Laniakea, the supercluster that is our home. And now, in this final chapter, we go further still. We climb one last time to the highest vantage point our science has yet reached, and we look out at the very largest things the universe has built. Things so enormous that even the word enormous is inadequate. Things so vast that astronomers, upon discovering them, found themselves questioning not just their instruments but the fundamental theories upon which all of modern cosmology is built. We are going to meet the titans of the cosmos, the great walls and arcs and rings of the universe, the structures that should not, by any reasonable reading of our current understanding, exist. And in meeting them, we are going to arrive at something that may be the most honest and the most beautiful thing that science can offer, the edge of what we know, and the vast, inviting, slightly vertiginous feeling of standing at that edge and looking out into what we do not yet understand. Let your breathing be slow and easy. Let whatever remains of the day's weight dissolve a little further. What we are about to explore is not frightening. It is wonderful. It is the universe being larger and stranger and more surprising than we expected, which is something it has been doing reliably for as long as we have been paying attention. To understand why these titanic structures are so significant, we need to understand a concept that cosmologists call the end of greatness. It is a phrase with a certain melancholy poetry to it, and it describes something very specific and very important about the universe at its largest scales. The end of greatness is the scale at which, according to our best theories of how the universe formed and evolved, the cosmos should become effectively uniform, smooth, featureless in a statistical sense. Below this scale, structure exists. Galaxies, clusters, superclusters, the filaments and voids of the cosmic web, all of it organized into the complex, beautiful, hierarchical architecture we have been exploring together. But above this scale, above a certain threshold of size, the variations should average out. The density should be the same in every direction. The universe, at sufficiently large scales, should look the same no matter where you point your telescope. This prediction is not arbitrary. It flows directly from the physics of the Big Bang and the way that the tiny initial ripples of density in the early universe could have grown under gravity over the age of the cosmos. There is only so much time. There is only so much gravitational amplification that can occur in 13.8 billion years. And beyond a certain scale, the structures simply have not had time to form. The universe has not been around long enough to build anything bigger than a certain size. That is the theory. That is the prediction. And for much of the history of modern cosmology, observations seemed to support it. And then astronomers kept looking. And what they found over and over again was that the universe had apparently not read the theory. The first great challenge came in 2003, when a survey called the Sloan Digital Sky Survey, one of the most comprehensive maps of the distribution of galaxies ever undertaken, revealed something extraordinary. Hidden in the data, stretching across the sky in the direction of several constellations, was an immense concentration of galaxies forming a structure unlike anything previously catalogued. They called it the Sloan Great Wall. And it was a wall of galaxies, a great ribbon of matter, extending for approximately 1.37 billion light-years. 1.37 billion light-years. Take a moment with that. We spent the previous chapter in awe of Laniakea, our supercluster, which spans 520 million light-years. The Sloan Great Wall is more than twice that size. It is a structure so vast that even Laniakea, in all its grandeur, would be a relatively modest feature within it. The Milky Way, sitting in the outer reaches of Laniakea, would be a single barely perceptible speck within the sprawl of the Sloan Great Wall. For a time, the Sloan Great Wall held the title of the largest known structure in the observable universe. It was an unimaginably vast ribbon of galaxies and clusters and filaments, a great bright band of cosmic structure draped across 1 billion light-years of space. Astronomers studied it and debated it and tried to understand how it had formed, how the universe had managed to build something that large within the time available. The answers were not entirely satisfying. The Sloan Great Wall sits uncomfortably at the edge of what our standard cosmological models can comfortably explain. But the universe was not finished surprising us. A later survey revealed another structure, somewhat less well known but no less impressive. The Boss Great Wall, named for the Baryon Oscillation Spectroscopic Survey that found it, is a complex of 4 massive superclusters connected to one another by thick, prominent filaments of gas and galaxies. It stretches across approximately 1 billion light-years of space, slightly smaller in extent than the Sloan Great Wall but remarkable for the density and complexity of its structure, the sheer mass of the matter it contains. The Boss Great Wall holds within it over 800 times the mass of the Milky Way, gathered into those 4 great superclusters and the filaments that tie them together, a single coherent system of interconnected cosmic structures spanning 1 billion light-years. And still the universe was not done. In 2013, working with data from a different kind of observation entirely, astronomers announced a discovery that moved everything that had come before it into a new perspective. They had found, using a technique we will describe in a moment, a structure so vast that it dwarfed even the Sloan Great Wall by an almost incomprehensible factor. They called it the Hercules-Corona Borealis Great Wall, after the constellations in whose direction it is found. And it is, as best as our current ability to measure can determine, the largest known structure in the observable universe. The Hercules-Corona Borealis Great Wall is approximately 10 billion light-years wide. Let that number settle. 10 billion light-years. The observable universe itself, the sphere of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. The Hercules-Corona Borealis Great Wall spans more than 10% of that total. 1/10 of everything we can see, in one direction, is occupied by a single structure. If you were to draw the observable universe as a circle on a piece of paper, and then draw this wall within it to scale, it would stretch from one side of your drawing nearly to the other. It is not a feature of the universe. It is, in some sense, a substantial fraction of the universe. Light, traveling at the ultimate speed of 300,000 kilometers per second, the fastest anything in the universe can travel, takes 10 billion years to cross from one side of this structure to the other. The universe itself is only 13.8 billion years old. The light that is right now crossing the midpoint of the Hercules-Corona Borealis Great Wall set out on its journey when the universe was less than 4 billion years old, when the Earth did not yet exist, when our solar system had not yet begun to form from the clouds of gas in a distant arm of a young Milky Way. And this structure, this 10 billion light-year wall of galaxies, theoretically should not exist. Our standard cosmological models, the same models that have been so extraordinarily successful in explaining so many things about the universe have genuine difficulty accounting for a structure this large forming in the time available. The universe should not have been able to build something this big. The end of greatness should have prevented it. And yet here it is, in the data, in observation after observation, an immense and stubborn feature of the cosmos that our best theories struggle to explain. The method by which the Hercules-Corona borealis Great Wall was discovered is itself worth a moment of reflection, because it is one of the most remarkable tools in all of observational astronomy. It was mapped using gamma-ray bursts. Gamma-ray bursts are, for their brief duration, the most luminous events in the known universe. They are the death cries of massive stars, or the mergers of dense stellar remnants, events so energetic that for a fraction of a second they outshine the entire galaxy in which they occur by factors of billions. They are visible with the right instruments across almost the entire observable universe. A gamma-ray burst happening 10 billion light-years away can be detected by our satellites and telescopes, a momentary flare of extraordinary energy crossing the cosmos to reach us. By mapping where gamma-ray bursts occur across the sky, astronomers can trace the distribution of massive galaxies, since gamma-ray bursts tend to happen in certain kinds of galaxies, and so their clustering reflects the clustering of those galaxies. And when they mapped the distribution of gamma-ray bursts in a certain region of the sky, what they found was a statistically significant excess, a region where bursts were clustered together far more than chance would predict, tracing out a structure 10 billion light-years across. A wall of galaxies so large it was only visible through the light of dying stars scattered across its face. There is something extraordinary about that image. We detected the largest known structure in the universe by listening to the death cries of individual stars, scattered across 10 billion light-years like campfires spread across a continent, each one briefly brilliant, each one marking a location in the structure, the whole pattern only becoming visible when you looked at all of them together and saw the shape they described. And then, in more recent years, the universe offered two more surprises. Both of them discovered in the same general region of the sky, lying billions of light-years away, and both of them deeply puzzling for the same fundamental reason that the Great Walls are puzzling. They should not exist, and yet they are undeniably there. The first is called the Giant Arc. It was announced in 2021, discovered in a survey of distant galaxies approximately 9.2 billion light-years away. The Giant Arc is a curved structure, a great sweeping crescent of galaxies and galaxy clusters and quasars, spanning approximately 3.3 billion light-years from end to end. 3.3 billion light-years, curved into a nearly symmetrical arc, like the crescent of an enormous moon drawn in galaxies across the deep sky. What makes the Giant Arc striking beyond its size is its shape. It is not a formless clump or an irregular concentration. It is a curve, a clean and graceful arc, nearly symmetrical, tracing out a form that looks almost deliberate, almost designed, in the way that the most beautiful things in nature sometimes do. Whether that shape has a physical explanation in the known physics of the universe, or whether it points to something we do not yet understand, is a question that is still being actively debated. It sits at a distance of 9 billion light-years, looking back at us from a time when the universe was only about 4.5 billion years old, and it presents its elegant crescent shape to our instruments like a question we have not yet found the words to answer. And the second surprise came in 2024. while analyzing data from the same general region of sky as the giant arc, astronomers found something that is, in some ways, even harder to explain. They found a ring, a nearly perfect circle of galaxies, 1.3 billion light-years in diameter, sitting at a distance of approximately 9.2 billion light-years from us, in almost the same region of sky as the giant arc. They called it, simply and appropriately, the Big Ring. The Big Ring is not a ring in the way a planet's rings are rings, not a flat disk of material orbiting something. It is a three-dimensional structure, a roughly circular arrangement of galaxies distributed in space, forming a shape that, when projected onto the sky as we observe it, appears as an almost perfect circle. A hoop of galaxies, 1.3 billion light-years across, hanging in the deep sky 9 billion light-years away. The existence of the Big Ring is, to put it gently, unexpected. The standard model of cosmology does predict that there should be a preferred scale at which galaxies are slightly more likely to cluster, a feature called baryon acoustic oscillations, an imprint left in the distribution of matter by sound waves that traveled through the very early universe before the Big Bang's fireball cooled enough for atoms to form. But the Big Ring is much too large to be explained by baryon acoustic oscillations. It does not fit neatly into any of the standard explanations. It is, like the giant arc near it, a structure that challenges us to think carefully about whether our current models are complete. And here is perhaps the most important thing to understand about these titanic structures, about the Sloan Great Wall and the Boss Great Wall and the Hercules-Corona Borealis Great Wall and the Giant Arc and the Big Ring. They are not embarrassments to science. They are not failures. They are invitations. They are the universe doing what the universe has always done when we have looked at it carefully enough, being more complicated and more interesting and more surprising than our theories predicted. They are the leading edge of discovery, the places where our maps run out and the unmapped territory begins. Every great advance in our understanding of the cosmos has begun with an observation that did not fit the existing theory. The expansion of the universe was unexpected. Dark matter was unexpected. Dark energy was unexpected. The detailed structure of the cosmic microwave background was unexpected. And each of these unexpected things turned out, when we understood it, to reveal something deep and true and beautiful about the nature of reality. The titans of the cosmos, these structures too large to fit comfortably into our current models, are pointing at something. We do not yet know precisely what. But the history of science gives us every reason to believe that when we finally understand them, what we find will be extraordinary. And so we arrive at the end of our journey together. We have traveled from the cosmic web, that grand and glowing architecture of filaments and nodes and voids, all the way out to the very edge of the observable universe, to the Hercules-Corona Borealis Great Wall and the Big Ring and the Giant Arc. Structures so immense they challenge the foundations of cosmology. We have passed through dark matter and galaxy clusters and Laniakea and the Great Attractor on the way. We have covered 13 billion years of cosmic history and 90 billion light-years of cosmic space, in these quiet hours of listening and drifting and letting the universe wash over us. And what does it all amount to? What do we take from it as we lie here in the comfortable dark, on the edge of sleep, one small warm creature on one small world in the outer reaches of a minor filament of a supercluster that is itself just one knot in a web of unimaginable size? Perhaps this: the universe is not cold. It is not indifferent. It is not a featureless void in which we happen to find ourselves by accident. It is a place of pattern, of structure, of breathtaking organization at every scale, from the smallest quantum fluctuation to the largest Great Wall. It has been building these structures for 13 billion years, from nothing more than the faintest whispers of density in a newborn cosmos, using nothing more than gravity and time. And the structures it has built are beautiful. The cosmic web is beautiful. Laniakea is beautiful. The giant arc, curving its 3 billion light-year crescent through the deep sky, is beautiful. The big ring, forming its perfect circle 9 billion light-years away, is beautiful in a way that goes beyond aesthetics and becomes something more like meaning. We live in a universe that makes rings, that builds arcs, that weaves webs, that organizes itself across scales of billions of light-years into patterns of extraordinary elegance, and then turns out to contain structures even larger and stranger and more surprising than those patterns predict. We live in a universe that is, at every scale we have managed to look at, more than we expected. You are part of that universe. You are made of the hydrogen that drifted in the cosmic filaments, and the carbon that was forged in dying stars, and the iron that was scattered by stellar explosions across the arms of a galaxy flowing slowly through the outer reaches of an immeasurable heaven. You are, in the most literal and physical sense, a part of everything we have described tonight. Not separate from it. Not a visitor to it, part of it, woven into it at every level, from the atoms in your body to the address of your galaxy in the cosmic web. And right now, in this moment, as the universe continues its patient, ancient work of building and expanding and surprising the people brave enough to look, you are resting. You are safe. You are held by the gravity of a small, warm world that has, against very long odds, produced creatures capable of wondering about great walls 10 billion light-years wide and perfect rings floating in the dark 9 billion years away. That wondering is not separate from the universe either. It is the universe's own capacity for curiosity, turned upon itself, using the instruments of a human mind to try to understand what it has made. When you think about the Hercules-Corona Borealis Great Wall, the universe is thinking about itself. When you feel the quiet wonder of Laniakea's name, the cosmos is experiencing its own beauty through you. We are not observers standing outside the universe, looking in. We are the universe, looking. Let that be the last thought that carries you into sleep tonight. Not a thought about distance or scale or the incomprehensibility of billions of light years, though all of those are real and true. But this simpler, quieter thought. You are the universe resting. After 13.8 billion years of building, of weaving the cosmic web and assembling the great walls and scattering the galaxies across the filaments and carving the voids and drawing the great arcs in the deep sky, some small part of it has settled here, in this body, in this quiet, and is breathing, and is letting go, and is, at last, at rest. The titans of the cosmos will go on turning without you tonight. The Great Wall will keep its watch across 10 billion light-years of dark. The big ring will hold its perfect circle in the deep sky. The filaments of the cosmic web will carry their rivers of dark matter and gas through the eternal patient silence of space. And somewhere in the outer reaches of Laniakea, On a small blue world orbiting an ordinary star, you will be sleeping, softly, safely, at home in the immeasurable heaven. Good night.